G'day guys, welcome back. Okay, so what I've done here is I've hooked a little bit of a rig up so you guys can see this a little bit better. We're going to delve into the panel meter issue here. I've actually hooked two of them up. What I've done here is this is the negative, the common terminal from my power supply, also the negative sense terminal. This is the positive regulated 12 volts. And this is the positive sense terminal from also the output of the power supply. So these two are what the meters are measuring. These two are what are powering the meters. I can demonstrate that by taking the sense wire out and putting it in here, and you'll see it's 12 volts. So 30.132. Oh, I really don't want to take my phone out the rig. You guys have seen in previous videos the display on my multimeter is reading, right now it's reading 30.114. This is reading 30.133, so it's off, and I could show you on the fluke just quickly. If we can get in here somewhere. 30.11, not 30.13. So there's a 20 something millivolt error there, you can see, even with the missing digit on the fluke. So the reason I've put both meters here and hooked it up like this is so that I can do the modifications I was talking about in the other video on one of them, and then you guys can see the comparison in the readout between the two, the unmodified one and the modified one. These are bang on. There's just a little bit of connection resistance, I think. They usually read like literally the same. It's a bit odd. Oh, well, I guess it's just the tolerance and the resistive dividers. But anyway, another discovery that I've made that has definitely convinced me that accuracy problems the resistive divider is this. If we power both the meters off of the sense voltage, 30, .132. Wait a minute. .132. .133. Okay, it's only a millivolt difference, but you can see that when you put them in parallel, which is what that's doing, it's effectively putting this resistive divider, basically the positive end and the negative end, that and that, in parallel with the one in there. And then, I don't know if you do the math on this, let's just say they're not, but let's just say this resistor is 100 ohms and this is 100 ohms, but in reality, because of the tolerance error, this is say 100 and this is 101, and that one, the resistor might be, one might be 100 and the other one might be, say, 99 ohms. When you put them in parallel, it kind of equals the resistance out and brings it closer to that lower percentage of error, like 100 ohms on both resistors, if that makes sense. So that's also how I've worked out that definitely it's the resistive divider. So what I'll do for now, whilst we're working, is I'll turn the voltage on my power supply down to something reasonable, just so if somehow I do something silly or any of this touches, it's not going to hurt the power supply. Power supply can handle shorts and everything. I've designed the crap out of that, but I don't want to blow bits of metal off of my alligator clips and all that stuff, because it'll just knock the plating off of them. They'll start to corrode and make poor contact, and yeah. Okay, second thing I've got here, the fluke. Obviously, when you're up at 30 volts, it's not displaying the millivolt, but you can still see the second digit is out by 20 millivolts. So that's fine for you guys to see the difference between the 2 meters, just to verify that not only you can see it on their displays, but you'll be able to see me measure the actual voltage here with the fluke, and it will match up to the meter that I fixed, and it won't match up to the other one, just like the meter won't match up to the other one. So that's to verify that we get this correct. The LCR meter here, I'll just move the meters off to the side for now so that I've got some space to work. The LCR meter, what we're going to do with this is not for these resistors, because we already know they're crappy tolerance and they're not bang on right. There's no point in measuring them. But when I go to replace these with metal film 1% resistors, and I'm not just going to pick the value and put it in, we're going to measure the resistance on a high accuracy resistance meter so that we can actually get the resistors down less than 1% tolerance. What I mean by that is with 1% tolerance resistors, say again you've got a 100 ohm resistor, if it's 10% tolerance, or whatever 10% of 100 is, which is what, 10 ohms, a 10% 100 ohm resistor could be anything from say 90 ohms to 110 ohms. Obviously a 5% one would be 95 to 105 ohms, a 1% one would be 99 to 100, sorry, a 1% one would be I think 99 to 101 ohms. You get what I'm getting at. My maths is honestly terrible. It's amazing I do this crap with the math skills I've got, but with calculators and just understanding what the actual formula is, I still managed to get there in the end. Anyway, so say I select my 1% tolerance resistors, I can then measure them on this and say, okay, this one's 99.8 ohms, this one's 99.9, this one's 99.8, this one's 99.7, this is 101.2, this one's 99.8. Hey, that one was 99.8 too. So then we'll grab those two resistors, and now we know they're literally matched to like 0.1% or somewhere around that ballpark. It'd be 0.1, 0.2% going off the accuracy of this meter. So then we've just effectively turned our 0.1% resistor into, sorry, our 1% resistor into a 0.1% resistor. That's what we're going to do to get the accuracy on here. So now I've gone over what's going on, our supplies, our test setup, what one meter's for, what the other meter's for. I'll move this meter out the way for now too, because we don't need that now. Let's get into it. So what we're going to do is we're going to pop this board out of here. Now, when I bought these, because every time I buy a product, I do a complete teardown on it myself, because I want to inspect the quality of it, you know. There's a lot of these panel meters online where the actual microcontroller is sanded down. There's different part numbers on the op amp. Also, I just want to go into this. The other night, I wasn't really thinking, and I only had a quick look into this, but when I finished the video, it hit me, and I thought, man, I'm silly. The way this thing's working, obviously, there's not many components on here, but let me just get something to point. It's got a single end on it. Obviously, that's your resistive divider that divides the sense voltage and ground, and the midpoint goes into obviously the one of the inputs on the op amp. The other input would have a reference that would be supplied from this microcontroller. The output of the op amp would go into a DAC that would be inside the microcontroller, and the microcontroller therefore is a microcontroller, a DAC, and a voltage reference in one package. So you got your power coming in, a little bit of filtering, diode so idiots don't install it the wrong way around and fry everything. a LDO 3.3 volt regulator and its filter cap to supply the voltage to the micro, couple of resistive divider networks for the multiplexing the display from the micro, and then, as I said, then the micro provides a reference voltage to this op amp, which is basically acting as a comparator, and it's comparing the reference voltage, which is our sense voltage, which is divided down to a smaller voltage to be compared against the reference voltage, and then the output of that will go into the DAC in here and be spat out as numbers on the screen. So this is a high accuracy part. It's not the problem's not in here. The problem's certainly not in this op amp or the stability of the reference on here, because I've checked the accuracy like I showed you in between 0 to about 12 volts and it's bang on. And another phenomena I noticed is when I've got the voltage down lower around say 20 volts, if I hook up two of these guys in parallel with the sense wires in parallel like I did here, and powered off the same supply rail, that obviously adds some resistance, and the added resistance from the supply rail resistance and the two resistive dividers being in parallel, as I showed before, was making these display a bang on accurate figure. So I'm 100% it's the resistive divider network, which I'm really happy about, because I was hoping that, like the screen would have enough digits. It does. That's why I ordered it. I was hoping the micro or whatever controlled it and the op amp would have the resolution I needed. It does. So that's all great. I don't need to worry about that. So that being said, let's pop it out. Might have to just, there we go. So there it is. There's your screen, shield, whatever you want to call it. Make it look nice. There's your 5-segment display. They advertise the shop that these are being sold off of on Taobao. I actually bought this off Amazon, but wow, that's hilarious. They haven't even peeled off the bloody when you buy the brand new panel meter, it comes with a protective sticker. They didn't even peel that off. Anyway, there's a lot on eBay that are not made by Readon and have the chip sanded down. I got this off Amazon. It's got the genuine ST and says it's made by Readon. Whether it is or not, who knows, but the way it performs, I'd say it is. So that's why I chose this one. So what we're gonna do, trying to decide if I want to use hot air or just a soldering iron to take these off. I think I'm just going to take the soldering iron off because I don't want to heat the whole board up. We don't know how sensitive to temperature this device is here. These little caps don't like to be heated up. I don't want to melt the plastic on here or this plastic. I'd have to shield everything with Captain tape and bits of foil. Honestly, I think I'm just going to swipe them off with a bit of solder and a normal tip. So we don't really need to take note of which resistor goes where because we've got another meter or two. We've got the one in the power supply and one there. So if I forget the higher value resistor where it goes and the lower value resistor, I can just look on the back of that. That's not a problem. So what we'll do is we'll just come in and flood that end with some solder, flood that end with some solder, and then just swipe it off, drop it on the bench, come in here and do the same thing again, Sorry about my shaky hands, guys. It's actually not because of me recording videos on YouTube. It's not stage fright, if that's what you're wondering. I've got a few stresses going on in my life at the moment. Some different issues. I'm trying to start my own company. I've recently gone through some legal trouble. My missus is having some problems also. Well, we're not having problems between us, but basically earlier on, I don't want to go into the details on this, but earlier on, a couple of years ago, my missus wasn't well. She's fine now, and we got into a few fairly heated arguments because she thought I was doing stuff I wasn't doing, and the police, in all of their infinite wisdom, thought instead of trying to help us or help her or offer counselling or something like that, they thought they put AVOs on us. So then they put a 100-metre condition on her AVO. She lives with me. She doesn't have anywhere else to live. So they made our life really hard. So we've had to spend money on lawyers, try and sort it out to change the AVO conditions. Like I said, I've had my own stuff going on. Personal problems in my past I don't really want to go into great detail with you guys, but I'm not going to hide it from you. My previous life, I'm 32 now. When I was younger, I grew up on the streets basically. I used to live at home with my mum. She was a Jehovah's Witness. I don't know how many of you guys know or are familiar with that religion, but in my words, I would describe it as a cult. I wasn't allowed to celebrate my birthday, Christmas, have friends outside the religion. Everything was just, I didn't have technology, nothing. It was just, I couldn't even watch half the stuff on TV. So my childhood was very different growing up. And then when I hit 13, I didn't fit in with the kids in my own year and the year above because they used to just pick on me because I was different. And the older kids in the older school years, they would hang out with me, but unfortunately they were a bad influence. They were all smoking cigarettes and pot and drinking, so I fell into that. And then I started hanging out with their cousins and their uncles and that, who were doing harder drugs, like meth. And I ended up doing that at the young age of 13. Got out of that at the age of 17. Became hooked on the alcohol for about 2 years. Got off that, and then one New Year's Eve night, I don't know why, I was like, hey, I'm just going to do a little bit of meth this night. Dumbest decision ever, because what happened was I ended up doing it again the next fortnight, and then the next fortnight turned into the next week, and then the next week turned into every couple of days, and before I knew it, that was another year or 2 year run, and then I'd finally just had it. I'd started smoking heroin, got off that using Bupe and Valium, if anyone knows what that is. It's good stuff it's, in my opinion, look, it's the best way to get off the stuff. If anyone out there is actually like requiring help to get clean or wants advice, feel free to reach out to me, because I can tell you how to do it in your own home. You won't have to go to rehab. You won't go to a drug clinic that will put you on methadone or something like that will just ruin your health. The other thing the drug clinics do is they don't tell you that you can use Bupe for 5 to 7 days and not get addicted to it, and actually cut down on your heroin to the smallest possible dose you can take, and then use Bupe for 5 to 7 days and taper down on that, and then take, say, Valium for a week just for the last few symptoms you got left, and then you're clean. You go into a drug clinic, they'll put you on some dose at some level. You'll go back the next fortnight or the next week, they'll up the dose. Not only they will up your dose, but they'll dose you happily for weeks without telling you that you can only take the stuff, for example, Bupe, for 5 to 7 days without actually becoming addicted to it. So most people go to drug clinics and they end up stuck on Bupe for life, or stuck on methadone for life, which destroys your body. Does terrible things. It causes fluid retention, destroys your bone density, mucks up your liver. It's just terrible. It's just terrible stuff. The butte doesn't do that so much. Like most opiates, it just sort of dehydrates your body. That's probably one of the worst things it does. But yes, if anyone does require help with that, please feel free to reach out to me, because I would be happy to give people advice with that sort of thing. But that's my background, you know. My life wasn't perfect. Now I'm trying to do this. I'm 32 now, so like, you know, this was a long time ago. But I digress. I just wanted to go over that. I don't want to hide it from anyone. That is my past. Who I am now is a different person. But it is what it is. At the moment, as I said, my current stresses are basically just all the years of doing that stuff sort of destroyed my health a little bit, and that's caused me stress trying to get that back. Trying to start my own company right now. I've just reset up my ABN, reset up my bank account, sorting out my tax. I let a lot of things go over the years, ended up in debt, and yeah, so that's all the stuff that I've been trying to fix up the last couple of years, and that's why I'm stressed at the moment. So when you guys see me a little bit stressed, don't worry, it's not you guys at all. It's just my own life. I'm getting there, so don't worry. This is helping me greatly because this keeps me occupied. This is what I genuinely like doing. So yeah, don't worry. I digress. Let's get back to the actual video. So we've got these two resistors here. What we're going to do is we're going to measure their reported values on the multimeter versus their actual values. So the way we're going to do this, for those that don't know, SMD resistors have numbers on them. If I just bring one of these up to the camera, okay. There you go, 3303, I think it says. I'll have a better look with my own eyes, it's hard looking on the screen. But anyway, so the way you decode that is the first digit is the first digit, the second digit is the second digit, the third digit is the third digit, the fourth digit is the multiplier. I think SMD codes sort of vary, they get me. So it should be 330, so 330 ohms with another 3 zeros, so 330 kilo ohms. Let's see if I'm right on that. Yeah, that's something I hate. That's why I have LCR tweezers for SMD components. Yep, 330 kilo ohms. But you'll notice it's gone. I did hear where that landed. I'll have a quick look and see if I can spot it. But these resistors are going, so I'm really not concerned. Oh, there it is, I found it. Like I said, I've got ridiculous hearing. Well, I didn't say that, but I do. Can really pinpoint sounds quite accurately. Anyways, that came in at 328 kilo ohms. What's this other one say? So that one says 2002 or 2802. I think it says 2002, so it's going to be 200 with 2 extra zeros. 200 ohms, 2000 ohms, 20k. $19.99k. So that one's almost bang on, and that one's out. I had a funny feeling it was going to be the positive side, but I was actually thinking of like just leaving them on there and putting a trimmer over the positive side one and trimming it. But then I thought, look, the trim is going to be a carbon film. The resistors I'm going to put a metal film. The carbon film has, I think, a negative temperature coefficient, and the metal film has a positive temperature coefficient. I'd rather the temperature coefficient just be the same for both resistors, because it's a divider. If one's negative and one's positive, the values are going to change as the temperature changes, and the resistive divider is not going to be equal on each side, and it's going to lose its accuracy. But if both the resistors change value at the same time, the midpoint's still going to be the exact same voltage and you won't lose accuracy. So I thought, okay, I'll just take them out and replace them with high tolerance resistors first. So we know we've got a 330k resistor. And a 20k. 20k is on the negative side, 33k is on the positive side. Stick that off over there. Can you guys still see that? Yeah, cool. Alright, we're getting somewhere. I am now realising that I should have measured these resistors in advance so I could go and sort out the resistors, but what do you do? Okay, so 20k I might not actually have in metal film. So I might have to change the ratio. It's going to take a little bit of math. Do I have 2k? Let me just go have a very quick look on my E12 resistor chart. Because I've got the, I think it's the E12 series range from J-Car. That. Okay, so where's our Ks? 22k, 18. Do we have 2k? 2k2. Bummer. Okay, well, okay. Like I said, it doesn't really matter if it's positive or negative Tempco resistors, as long as they're both the same. What I do have is I've got little quarter watt 5% carbon film resistors, and we can still effectively turn them into 1% resistors, 0.1% resistors. It's just going to mean that I'm just going to have to go through a lot more of them and match them to get the exact close value that I'm after. But that's okay. We'll do that. I'll just grab a box of quarter watt resistors that have got 170 different values. So first resistor we need is 20k. Excuse me, I'm just looking at my resistor color chart. I always forget half the colors. You know, like half the colors I just automatically remember, like a 47k, I just know it's green, purple, orange, red. You know, like 100 ohms gonna be brown, black. You know, depending if it's 4 or 5 bands, it could be different. But anyway, you know, like there's so many values, 560s, you know, green, blue, black. And then there's all other things that I just randomly forget. It's just, I find if I'm working on something I'll sort of get used to all the color codes for the project I'm working on, and then because that's gone on for so long, by the time I start working on something else, I'll start to forget the color codes again. So always just keep a color chart in front of me. What I mean by that, I'll just show you guys quickly. That guy there, so you can understand what I'm looking at. Let's try and get this back where it was. I think that'll do. Right. So 22K is going to be red, 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 I think. Yeah, these have only got 3 bands on them, so I think that's what it's going to be. Sorry, red, red. Yeah, red, red, red. Oh no, that's 22. Sorry guys, I need 20. So if you want red, black, I want 20K, don't I? Sorry. So I want red, black, red. Okay. Alright. Red, black, red. I knew something was off there. Yeah, so that's why I keep the resistor chart in front of me, because it just gets ridiculous. And yes, I know I need to sort all these resistors out. But at the moment, as I've shown in my lab tour video, don't have too much space in here at the moment, so everything's just kind of crammed in where it fits. It's always the one you're looking for that just takes forever. I paused the video. Okay, you know what I'm going to do for you guys, because I don't have video editing software. I don't want to stop the video. This is going to take forever, because what I want to do is I want to get a few of the 20Ks and a few of the 330Ks so that we can measure them on the LCR meter and get them dialed into that close to like 0.1% value. I'm just going to pause the video whilst I find the resistors, because I don't want to bore you guys with me just looking through a box. I've actually got 2 of these boxes. So I'll just pause the video quickly and then I'll resume it in a minute. Alright, sorry about that guys, this is taking so long to find them, it's not funny, I don't know why. I'm just having one of those days. I already took the closest value resistor out of the packet out. As you saw, I got 2 boxes. Saved you guys some time. I found one that's bang on 20.01 k ohms. Let's go through this one. So we've got 19.84, 19.84, 19.84, 19.70. It's just a strange thing. It doesn't look too promising, and then all of a sudden you hit bang on. 19.80, 19.74, 19.70, 19.87, 19.88, 19.80. That's the only one that I've found so far that's close to 20. So I'm going to put these, excuse me, these 2 boxes back away. Actually, no, I'm not. I'm going to pause the video again because I've got to find the 330Ks. So I'll be back in a minute. Alright guys, we're back. I found the orange yellows. It took less time, so I'll just go through them both. Can we see the meter? That helps. Right. 329.3, 326, 335. See what I mean, guys? Hey, 330.3, we'll take that one out. 332, 328.9, 325.7, 329.4. Take that one too, you'll see why later. 327.5, 329.8. Take that one too. So these three are very, very close to 330. That's very close to 220. I didn't have any others that were only the last least significant digit out by a couple or 2 digits. All the rest were like like 20 and a half K or something ridiculous. This was the only one that was close. But let's not forget that when we measured this, because this doesn't matter now, these are all carbon film resistors, so we're not going to get screwed by mixing them and having different temp codes. So we could use a combination of any of these. So our 20K and our 20K, what we're going to do now, well, let me just put these resistors back away. That's the one thing about running a lab or a workshop, is it gets very, very cluttered and very, very messy, guys. And my best advice to you is keep the stuff you're working with on the bench in front of you, as you see I do. Everything else pack up as you go, because if you don't, within a week, you will not be able to fit in here yourself. It's, yeah, I mean, you can already see all the clutter everywhere. You've seen my videos. Anyways, let's take these two. Let's have a look at what the LCR meter says first. Yes, this is calibrated. Yes, I cleaned the jacks out. Let's just make sure. Let's try it at a frequency. I'm a fanatic. I like to make sure everything is reading perfectly. And you'd be amazed what some contact resistance does. Sorry about that bang, guys. Thing is, as you hook onto components, not only all the crud off the components ends up on these contacts, but you also slowly wear down the gold plating, end up back to brass, which oxidizes even quicker, obviously. And So then you've got to clean it even more. And yes, you shouldn't really touch it with your fingers, but oh, we're really not getting anywhere, are we? I want to see zeros. You know what, maybe when I cowed this thing, because the lowest I'm seeing is 004. Sorry guys. Okay, that is just the cable. Alright. I could cow that out. Anyway, for what we're doing, it's not important. We've got I might have to cow this and clean it up. Sorry guys. Do an open cow. Sorry about this guys, but I mean if you want to see how these things work and the nuances of contact resistance and how just a little bit of oxidation and dirt in your jacks and your plated terminals makes a difference, you can see. This will only take a minute guys. Maybe I should do this with a thick piece of copper and clip them on it. Oh well. This will be plenty enough for what we're doing here. Okay. Let's see what we're reading actually. Alright, that's a lot better. And I wouldn't be surprised if I... Yeah, there you go. Okay, we're cowed. Right. Can you guys still see that? Yep, cool. Let's take this guy. .95. It's a bit more accurate than the multimeter. Also, this is at 100 kilohertz. Like if we test it at 1 kilohertz, because resistors do have inductance. See? Bang on. So as the frequency rises and the inductance has more of an effect, the resistance goes up. Trap for young players in precision circuitry. Not this circuitry. We're just reading a stabilized DC voltage. I don't know why I just did that. I am never going to find that. We've got the 330 now. Oh wait, that's the 202. What? Man, I just tried sticking a small surface mount resistor in them, even though I have LCR tweezers for this. Don't rush, guys. Let me just pause the video and have a look on the carpet, because I didn't hear it land, so I've got a funny suspicion it's hit something soft. And there's not much that's soft in here, so let me just pause the video and have a quick look. Okay, I couldn't find it, but yeah, I'm not too worried about that anyway. Let's see what this 20k resistor sort of comes in at. 19.99, and this one 19.99, basically the same. So we'll use this. Let's go put this in my little SMD resistor box. Now the 330Ks, let's see what we've got here. The trick I'm using is to try and get this, because if you see the teeth go this way, so if we get our pin in across more teeth, we get a sharper, grippier contact, get a better reading, eliminate resistance errors. So that's coming in at literally 33.1k. $33.9. Well, I think you guys can tell that these two resistors are bang on with each other. So now you see what I'm saying about matching resistors out of even crappy 5 or 10 other 5% resistors, gold band. So you can still get close tolerances, and they're both carbon film, so they're both going to have the same temp code. So that's our resistors. That's way over 1/2 of the problem actually. Just leave this off to the side, you'll see why that's there very soon. Now, let's put these other two resistors back in my drawers. Let's see how we're going to mount them, because they're not surface mount, but we're going to mount them on here. They're small enough. Yes, this is not how you would do something for a product you're going to sell. No, it's not unreliable, it's just not professional. But for developing something, absolutely nothing wrong with this. So what we're going to effectively do is turn these into SMD resistors. I've screwed the top end of my flush cutters. That's good. Need to buy new ones. We'll still get this. There's our drop-in SMD resistor replacement, or one of them. Not SMD, but as I said, replacement. Mimicking an SMD. SMD is surface mount design or something like that. I always forget. But these little components, not these 3-hole components with the pins. 3-hole components are the ones with the leads, like these resistors. And most of the components I work with. And SMD is all the stuff you've got inside your laptops, phones, computers, LCD TVs, all that sort of stuff. The components on the back of this panel meter board, it's all SMD. Right, well, I royally made a mess of that one. This is why I always cut things longer than shorter. It's kind of hard to make stuff longer again once you cut it too short, but if you cut it too long, you can always shorten it. I think that'll do. Yeah, that'll do. Okay, so that's our 2 little SMD components. Soldering iron's gone to sleep. Just wait for that to wake up. Don't worry guys, I remember that the 330k goes on the high side and the 20k goes on the bottom. But, you know, even if I didn't remember that, who cares? Could just look at the other panel meter and I wrote it down here. Don't need this no more either. Okay, so let's just flow some nice leaded solder onto these pads. Nice 4 little leaded shiny balls there. So normally, I might be able to do this. Yeah, the phone sees it. Normally I'll use my helping hands. I thought the phone wasn't going to see it. I've got a set of helping hands and just one lone helping hand. Actually, this might be too small to fit in here. Okay, screw that idea. That's alright. Another trick is to just you know what? I'm just going to do this the hard way. It's going to end up being quicker. Come on. Don't do this. Don't want to get them hot and throw their values off. That's why I work with my soldering iron temperature turned up. A lot of people think 350 might be a bit hot, especially for leaded solder, but the thing is I don't want to get my component pins hot for too long because the heat will travel up into the component. And if I can solder it quicker, as you can see, the component's not hot. If you got to hold the soldering iron on there for a longer period of time with a lower temperature, yes, it's a lower temperature, but by the time you've got the pins soldered, the component's at that temperature too. Not what you want. So now we've got fresh solder on both. We'll just clean our tip. There's a bit of flux on the board there, that's all clean, that's all clean. So we'll just be able to reflow these in with a clean tip. So 20k on the bottom side, 330 on the top. Beautiful. Don't ever try and bend, if you solder parts to pads like this and it doesn't look perfectly straight, do not try and bend it, you'll rip the pads off the board, they're too small to withstand the force. If you really need to move it, just resolder it. I know it takes longer, but you won't be sitting there trying to fix ripped pads. This one's really not going to plan. Okay, cool. We've got them on there. So now I'm just going to touch them up a little bit more. Now that they're secured, we can solder one pin obviously at a time without it coming off the board. I am more than happy with that. So let's clean the flux off of there. When you're working with really high impedances, contaminants can get into flux if they're not already in it, and they can throw your resistances off and wreak havoc. I'll just wash that down with some IPA. One residue-free board. Sorry about that bang. Right. What do you reckon it's going to display? Just let that dry up a little bit more. put this back in because the rest of the work we can do with it in, I'm pretty sure. Beautiful. Alright, let's see what it reads compared to the other one now. Well, that didn't change too much, did it? But we're right down at the bottom end. I'm just going to wind this up to the top and compare it against my meter and the other meter here. Okay, so as we can see, that's actually gone in the wrong direction. And the beauty of the fact that I used carbon composition resistors is we can now trim the negative half of the divider with a trimmer pot and dial it in just perfect, because the trimmer pot's also carbon, so they've both got the same temper code. I guess I won't need this then. I was originally going to tack on a couple of wires to a breadboard and put a pot in it. Might still do that, just leave that just in case. But I'm just going to go take a quick break, guys. So I'll pause the video and I'll be back in a minute. We'll install a pot and we'll try and trim this to perfection. Alright guys, I'm back. So what I've done in the meantime, just to save some time, because I'm sure everyone here can see what I've done, is I've just soldered 2 wires across the lower value negative side of the voltage divider, and I've got a 1 mega ohm pot here. They usually set to about halfway when you get them brand new. Let's just see. Yeah, a bit under half. Okay. So just set that all the way to 1 mega ohm. There we go. And we'll put 1 mega ohm. I'm just going to go grab a 10 mega ohm and a 1 mega ohm resistor. Because 1 mega ohm might even be too much. We'll bend these wires so that we can have this facing you guys. You see that? Yes. Okay. So we've got one's reading 852, the other one's reading 853. Hold on a minute. Wasn't that reading too high before? Something's not right here. It's not some sort of capacitive problem. Is it because I turned the voltage down? And now it's reading lower. I thought I made it go the other way before it was reading higher. Okay, let's just see where we're at. Hold on. I'm going to wind the power supply all the way down. So the power supply is actually at 7.733. And the top one's more accurate. That's too low, the one I've just modified. Let's go all the way up. It's 30.1, that's 30.093. I don't think it's the negative resistor I've got to trim, I think it's the positive one. Yeah. Okay. How annoying. Could be worse, honestly. It's just one wire I've got to change the position of. It could be a lot more annoying. Okay. And we're across the positive one. I have to wait for that resistor to cool down. As you can see, as it's cooling down, the voltage is dropping. That's what I was talking about with negative and positive temperature coefficient. So some resistors, basically what that means is their value will increase when they get hot. Others will decrease when they get hot, and vice versa. Depends if it's basically metal film or carbon film. Different compositions have different temperature coefficients, basically speaking. Alright. That seems to have equalized out pretty well. Might drop another digital. Maybe 3. No, I think that's pretty well where it's going to sit. Alright, so we're aiming for 30.109. We've got 30.101. We'll start off with the 10 meg resistor in series with the 1 meg pot. Oh, that's way too much. Wow. Damn, and we're so close too. This was out by heaps before. Now it's only out by, we're at exactly 30.109 and this is reading 30.98. So before we had a 20 plus something millivolt error, now we're only a few millivolts, which is great. And it's consistently low all the way through. It's not perfect up to say 10 volts and then loses accuracy after. So those two resistors have definitely helped a ton. But I need to trim this top one. And 10 mega ohms seems to be, yeah, 10 meg, too much. Just for shits and gigs, anything we can really do right now is go get more 10 meg resistors, because that's the highest. Wait, I've got giga ohm resistors. Hold on. Just realised something. I might actually, between a pot and resistor, be able to trim this. was the giga ohm ones? I don't see anything that's giga ohm in here. Wait. Oh, nice of these. These are sub ohm, aren't they? Yeah, ohms. I have labelled on this box that I have giga ohm resistors in here. Oh, hold on. I can't measure it. Wait, I do. Give me 1 sec, just have a look at the colour bands. Yeah, that's 1 giga ohm, I think. Okay, what does 1 giga ohm do? $30.106. Oh my god, we're at 30.108. That's 30.106. Oh, so close. Let's get the LCR meter and see if that can read resistors that are in the giga ohm region. Unfortunately, none of my multimeters have transconductance either, so I can't work out giga ohm readings that way either. Actually, I haven't checked out if my new bench multimeter can do that. It might be able to. Anyway, let's. Oh, bugger. Let us see if we can measure these guys. No. All we know is that these are higher than mega ohms. Sorry, that was a mega ohm. Wait a minute, these don't appear to be ordered correctly, sorted correctly, sorry. Let's just measure. Ah, that's 1 giga ohm. So the one that's in there is a bit higher. Maybe 2 giga ohms, 5 giga ohms, 10 giga ohms. Maybe I've got 1, 10 and 100. I don't know what I can't remember what I've got in there. These color bands don't really make sense. I think that's purple and that's grey on the 3rd band, but let's see if we stick what should be something higher than a giga ohm in series with the giga ohm. Yeah, it definitely goes down. So if only I knew what value resistor that was. Let's continue. Let's grab one of the other ones. Let's see what this is going to do. Definitely getting close, but okay, that's just too high. 30.109, 30.114. What happens if we put a giga ohm in series with that? Or whatever this is. 111, we're looking for 109. Wow, that's 2 millivolts out. God, that is close. Like really close. 30.109. Hey, what's going on here? Where is this actually going? It's going down that way. Oh, it's all the way down. 30.110. 30.111. Okay, we need something higher resistance than that. What does a single gigaohm do? I need 30.108, 30.109. .101. Okay. Getting close. No way. There you go. Bang on. My multimeter is literally on the edge of 108 and 109, and that is just jumping between 108 and 109. That's wonderful. Well, if we put one more mega ohm in series, does that? Well, I think that's bang on. That literally is flickering basically the same as my multimeter, which is 55,000 counts. Okay, let me just put these high value resistors back away before I get them mixed up with other value resistors. Man, the bands on these are just impossible to read. Those can go away. Man, it's dropped lower. Oh, my multimeter is actually reading 30.107. I'm not making this up, guys. There it is in the back, 30.107, 30.107. This is literally perfect. So, I'm in a good mood now. The only thing that I'm worried about is that when I turn it down, it's not going to be accurate. So let's see. What do we got? 15.593. Yeah. Let's see. .732 or .734. Oh no, .733, .731. Okay. Maybe when we solder all of these together. The contact resistance will be a little bit better. I think for the sake of a couple of millivolts, I'll just go with it. Let's see, if I turn the voltage up a little bit, 4.17, 4. It's honestly bang on. It's off by 3 millivolts there. Oh man, this is annoying. Values have we got here? They're all the same value. Let me go get one more of those. We might just might be able to get this perfect. It's a different colour. Nice is these ones. Oh no, that's green. Well, that is a higher value. That's off by 1 millivolt now. And you know what? That's on the end of wires and stuff. I dare say that would be it. Let's go back up. Please, 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 please be on. Damn it. Yeah, that brings back the initial 20 millivolt error. 30.105, 30.104. And as you turn it down, seven three 0732. So that's a 2 millivolt error. When it's closer, it's going to be high. You know what? I think for now this is the best we're going to get out of it, honestly. If I had more resistors to play around with, especially higher value ones, and more of the 330Ks and 20Ks to closely match, I reckon we could get it bang on. It is obviously, as I thought, the resistive divider, because as you can see, the other day this was off by like 25 millivolts. Now it's off by a maximum of 1 to 3 millivolts. I think I'm just going to go with that. This is only my own personal supply in here. Obviously, when it goes into production, I'm either going to use the same meter and build a better resistor network that's precise as, or find a better meter, or roll my own. So, considering it's just going in my own supply, I think I'll leave it at this. I am more than happy with that. It's through most of the range, it's accurate. It's actually right on. Most of the voltages that you use, from around about a couple of volts up to about 20 something volts, it's literally on. It only is at the top end it's 1 millivolt out, at the bottom end it's 3 millivolts out. When I put it in the actual enclosure, it should read 1 millivolt higher, so I think it'll have a 2 millivolt error at the most, which is funny because it was actually advertised as having this ridiculous accuracy of like 0.00 something % or even more, but then it said plus minus 2 least significant digits. Well, funny thing is that's basically what we've got now. So I guess they weren't lying about the chipset and everything in there, but they've used a crappy resistive divider network and it threw the accuracy up. So there we go. Also, just to point out, you could probably play around swapping these resistors with other ones, but I don't think it's going to make such a difference because these, what do we got? A brown, black, purple, and green, black, purple. What's the green, black, purple? 5. Yeah, that's what I thought. I'd have 1 5s and 10s. So we've got a 5 giga ohm resistor and 2 1 giga ohm resistors. You know what? Let's play around with the 1 giga ohm resistors. Yeah, you know what? Why not even play around with the 5 giga ohm resistors? I did say that I would shoot videos showing everything and not hide stuff, like the annoyances and nuances, like sorting out a product that's supposed to be right, that's not right. You order it, you just want to put it in, it doesn't behave the way it's supposed to behave. Okay, so let's take a couple of random ones. I'm not going to spend all day on this, but let's just see if we can get it to read 0.732 by substituting some of these. Not seeing any appreciable difference, like I said, because these are up in the giga ohm region. Even if they're like 5% tolerance, which they are, or maybe 10 or even more, the difference between them, I can't see it affecting it too much. See, that last resistor doesn't even have any effect on it until we go all the way up to the top. I'm pretty sure. Yeah, it's bang on accurate there. Oh, so there's no error at the top. The error is only at the bottom. Would be nice to have that the other way around, but again, it's only a 2 to 3 millivolt error. Alright, that's enough playing around. Put these guys back away. Let's get to work. So we know what we're doing now. Those 3 resistors we're going to put in series as close together as to each other as we can to save space. And where these 2 wires are across the top divider resistor, we're going to solder them across that, and that's going to be our modification for the accuracy of this thing. So there we go. I'm so glad it was just a resistive divider. And like I said, this can clearly be improved. It's not like I'm using high accuracy resistors or anything for this. If I can get it this accurate, you can imagine if I order a precision network, this thing will be bang on. It's wonderful. Oh, I see, I just went into a whole bunch of plastic. Oops. Alright, those wires can go away. They can sit there. Straighten these guys out. Oh, my cutters are not gonna get in there. How annoying. I don't like that. That's better. Sometimes it's just easier to cut in straight lines, and actually, you know what? I'm just going to do that. Screw this. I know a lot of people are fans of J-hooking because it's stronger, and if the solder cracks then the component connection won't fail. That's a load of bullshit, because if the solder fails, let's face it, there's oxidation and crap building up anyway. I mean, it might stop it from falling and touching something else in the circuit, but you know, this is fine. So that saves a lot more space. we'll put the high value resistor in the middle. These are all in series, there's no reason for this, it just looks cool. And it's what you want when you solder stuff. It should be nice and shiny, and you shouldn't see any bits of pins sticking out or anything around it. I'm just going to get a little bit of heat shrink to put over that. Yeah, I know I should have done this before I bent the legs. I only realised as I was doing it, I was like, ah, man, should have put some heat shrink on there. Better late than never. Come on. Yes. There we go. Let me get our leads nice and snug up. Don't think we're going to have any problems connecting that. Just shrink the heat shrink up. Crop our leads. Turn our voltage down so solder splashes on that, we don't get a big bang. Now what we'll do is we'll plate these, tin them, whatever you want to call it. perfectly happy with that. Just move this one off so it doesn't hit the side when it gets installed. Oh yeah. Oh yeah. So, what I'm going to do now, obviously, is I'm going to swap out the panel meter that's need to unplug my phone. I'm going to swap out the panel meter that's in there for the one that I've modified. That's it. In the next video, we'll be doing something else. So there you go. That is how, I told you it was around 732, 733. That is how we have got the accuracy back on this guy. So there you go, guys. Catch you in the next video. Peace.